We're getting into some very interesting territory here. We're going to deal with improper integrals that have infinite integration limits. First, let's define what an improper integral is. They're very improper. They have terrible manners. Ha-ha. Anyway, they have one of these two things, or maybe both. An infinite limit of integration. Let me define what that really means. Let's use the purple pen. The selection of colors is always such a massive idea, a massive ordeal. It would be something like this. An infinite limit of integration. It could be that, or maybe it could be from negative infinity to a or b or whatever. It could be this. It could go from negative infinity to infinity, actually. Or they're on an interval that contains an infinite discontinuity. For example, it could go from negative 1 to 1 of 1 over x dx, which, by the way, that one would not have an actual answer. But it could be a situation like that because 0 has an asymptote, right? So it's going to be like, oh, approaching 0 and, approaching the y-axis, and it creates this asymptote. So we have an infinite discontinuity on that interval from negative 1 to 1. So that's an example of that one. So let's just kind of work through the very first one we're going to see, and then we'll talk about some of the specifics of how to set them up. So let's consider this integral from 1 to b of dx over x squared. Now let's just talk about the fact that this dx, going old school here, it's the same thing as 1 over x squared, and then the dx is over on the side. The notation could go either way, just based on the way that we deal with fractions and the things we know about fractions. So I want to know what happens as b approaches infinity. Well, first of all, this is 1. If it wasn't set on the graph, now it's there. I want to know what happens if I was to color this entire area all the way to infinity. And it's clear that the function is getting closer and closer to the x-axis, clearly an asymptote. And if I colored all this area, how much ink would it take? How much pencil would it take? How many square units would it take to color all of this forever and ever and ever? If I extended this and I colored all that stuff. So this is going to go further and further. Let's consider what happens as b approaches infinity. Here's what I'm really saying. What I need you to do is find the integral from 1 to infinity of 1 over x squared dx. Well, you can't do that, okay? You can't go to infinity. But what you can do is find the limit as you approach infinity. And I say you, meaning you, the individual, but we're going to use the variable b. I generally use a for this one down here and b for that one up there, so 1 to b. Most textbooks do that as well. So this is basically this problem, but now we're going to say, well, let's just approach infinity. So it's 1 over x squared dx. And just to be clear about it, what we really are going to do is do a little rewrite here so we can integrate this thing better. At this point, you can do a lot of these in your head, but just be careful. I choose not to do it in my head because I'm the one explaining it. This is x to the negative 2 dx. We'll put a 1 there just for fun. And we are going to have the limit. You keep that limit going with you until you have evaluated it, and we have not. So we're going to have the limit as b approaches infinity. We're going to add 1 to the exponent. Old coefficient divided by new exponent, that gives me negative 1. And this goes from 1 to b. There's our fundamental theorem of calculus again. All right, let's proceed with this. And you don't have to write this next step, but I think it's going to help us to continue to articulate what's happening. Basically, nothing is different that you've done, only there's a limit hanging around, and that limit's approaching infinity. So in a minute, we'll use some of our knowledges, plural, I guess, our knowledge of what happens around infinity or as we approach infinity to figure the rest of this out. Because I couldn't just be like, well, how much ink do I use? That doesn't really help. So I have the limit as b approaches infinity. I'm just going to rewrite. So negative 1 over x, I think that's going to come in handy, from 1 to b, running out of space. Big process, huh? And that's going to be, well, the limit as b approaches infinity. At this point, we're going to use, well, fundamental theorem of calculus. That's where I plug the b's in, but we're not forgetting that we have limits that we're dealing with. Negative 1 over b minus negative 1 over 1. Okay, something very obvious is about to happen with this term, clearly, and I had minus a negative, so that's where the plus came from. So I really have the limit as b approaches infinity of negative 1 over b plus 1. So the limit really only applies to the stuff with the b in it, the term with the b in it. That would just be the first term, not the second term. Really running out of room now. Okay, if I plugged in, air quotes, plugged in infinity into the denominator, I would have -1 over enormous, like as enormous as it gets. -1 over infinity, that's practically 0. So I have 0 plus 1. So here we go. Surprise, surprise. 1. All this area forever and ever and ever and ever. If this was in inches, it would be 1 square inch. You would have enough ink to do it if you had enough ink in your ink pen. It doesn't require an infinite amount of ink is what I'm saying, which is really cool. Because we have an answer, I'm sliding all the way down to the bottom. We're going to skip this stuff for a minute. Because the limit exists and it's finite, the improper integral is said to converge. Converge means it comes together. That is about the best handwriting I've ever had right there. I'm just going to retire after I write that. There we go. I'm not even going to finish the video. That's it. That is the neatest handwriting. Sorry, I can't get over how neat that is. So the limit exists and it's finite. The improper integral is said to converge. Converge comes together to an answer. Con, the prefix con, means together. You have a conversation. You come together with someone. If you are, I can't think of another one other than a conversation. Anyway, converging comes towards a number. However, if I was to get off topic, as I did a minute ago when I noticed my lovely handwriting, I would, and now the pressure's on to write this one neatly, I digressed. Di, the prefix di, means away. So the limit does not exist or is infinite. The improper integral is said to, oh goodness, here we go, diverge. Ooh, not as good. Not tragic, but not as good. So diverge means it goes away from a specific value, so it does not exist or is infinite. Let's check these three out right here. If a function is continuous on the interval from a to infinity, then we just did this one actually, and it goes from a to infinity, but I can't go to infinity, so I have to write it as a limit, and alphabetically we'd put the a here and the b here. That's exactly what we just did. Notice that we had this, I'm trying to point here where the shadows aren't everywhere, but we had this, and then we said, well, you know what, I can't really go to infinity, so I'll just approach it instead. Okay, well, perhaps, maybe, we have a situation where we are approaching negative infinity, where we want to evaluate at negative infinity, not that we could, which is why we approach negative infinity. And we'll use a for that one. You can use whatever variable you want, but the convention is a and b. Now, if we are continuous on an interval from negative infinity to infinity and we want to evaluate both, we can do both of these, but break them apart at some value in between negative infinity and infinity, which would be any number. I'm going to call it c. So basically, I want to evaluate some function, the area between that function and the x-axis for all of its domain of all real numbers. I'd have to break it up into two pieces, from negative infinity to c and c to infinity. I would have no choice but to do it that way.